Guys, this video is a continuation of my last video when we were exploring properties of polynomials, but specifically, when solving them, finding zeros, we were talking about the rational roots test, which actually gave us a place to start, or at least a list of possible real rational zeros that might be zeros for the function. Okay, so we're going to kind of pick up where we left off here and say, okay, so let's go ahead and start with this function f of x. Okay, so now f of x being a third degree thing, again, this first thing I pointed out in the last video, but it's third degree thing. We want to go ahead and acknowledge and accept that we're going to be dealing with something that has exactly three complex roots. Okay, so it's possible that maybe all three are purely real, maybe just one of them is purely real, but they'll all three be complex. Okay. And so, on a different note, what I'm actually going to do in this video is I'm going to go ahead and start by graphing this on the grapher here, which is going to give us kind of a good idea of what this kind of behaves like in the first place. Now, keep in mind as I'm putting this in, the whole intent of the video is to learn to solve for zeros of a higher degree polynomial function without necessarily having a graphing utility, okay? And so we see here we have our graph, and it runs straight through x equals 1 right in here. So it's going to have one real zero and two complex roots, but I bring this function up for a reason, and so it gives us a good start. So we're going to go back over here. We say, okay, so first things first, if we were doing this without a graphing utility, the very first thing we'd want to do is do the rational roots test to get a good list of possible rational zeros for this. So we say, okay, so the rational roots, remember, were of the form p over q, where p was all the factors of the constant term, which in this case is 4. So we'll say the factors of 4 are 1 plus or minus 2 plus or minus, and 4 plus or minus, over all the factors of 3, which are 1 and 3, plus or minus, okay? So writing this out in roster notation, we have plus or minus 1 over 1, okay, plus or minus 1 over 3, plus or minus 2 over 1, plus or minus 2 over 3, and then plus or minus 4 over 1, and plus or minus 4 over 3. Okay, so a lot of writing, as a matter of fact, okay? But taking a look at this list, we know already from looking at the graph of the function that x equals 1 is almost 100%, no doubt about it, a zero of this. What I'm trying to do, though, in this video is illustrate a point, okay? And that point has to deal with what we're going to call upper and lower bounds for our zeros, or at least our rational zeros, okay? So what I'm going to do is I'm going to, oops, wrong key. I'm going to direct everybody's attention. I'll switch over to a bright color here. Direct everybody's attention to this list of possible rational zeros. And I'm going to pick something that, on purpose, I know is bigger than any of the real, the zeros of this function. We say 1 is the largest real zero of this. I mean, if we were to test anything bigger than 1 over here, first of all, it wouldn't work. It wouldn't be a zero, but it would clearly be bigger than the biggest zero of this function, which is 1, okay? So I'm going to pick 2, and I'm doing this to illustrate a point, okay? So let's say, I'm having a, working on my math, and I choose 2, and I say, okay, so I want to see if 2 goes into this, and of course I didn't have a graphing utility, of course, because if I did, I wouldn't use 2 in the first place. We say 6, negative 4. We say, okay, so let's carry down the 3. We say 2 times 3 is 6, 6 plus this negative 5 is 1, 2 times 1 is 2, plus 8 is, or 6 is 8, and then we say, okay, so 16 plus this 4 is 12. But what I want you to really realize is this. We put in a positive potential zero, okay? Of course, we knew it wasn't going to work. But we also knew this. It was bigger than all zeros that actually exist. In this case, 1 is the only zero. I know 2 is bigger than 1. It's greater than 1. So when you stick a positive zero out here, a potential zero out here, and this whole last row comes out to be positive numbers, something interesting happens here. It's just that these numbers in here get so large that they would necessarily have to overwhelm anything that would have been negative up here in the first place, causing this whole last row to come out to be positive. So what this allows us to do is necessarily say, okay, so if I put in this 2 right here, and it's positive, and the whole last row comes out to be positive, I know that not only can positive 2 not be a zero, okay, but anything bigger than positive 2 could also not be a zero. There's no way that positive 4 could be a zero. So, likewise, what we can also do is take into consideration that, okay, 1 is the only zero of this, the only real zero. But if we were to pick something less than 1 and try it, okay, I want you to see what happens when we pick something less than the least biggest zero of a function. So 1 was the least large zero of the function. Man, I hope that makes sense. So we'll pick something like -1 and try to use it. I just want you to see what occurs, okay? So we say, well, what if we had tried -1? Okay, so -1, we try it, and we say, okay, so all the original coefficients, 3, -5, 6, and -4, okay? We'll go ahead and carry down our 3 here. We say, okay, so we plugged in a negative number out here this time, a negative. So we say -1 times 3 is -3, and we say, okay, so plus -5 is -8. Times this -1, it switches its sign back to positive here, and I'm adding it to a positive. We see it comes out to be 14. So our 14 is positive, but when taken times a negative, of course, it switches its sign, and we say, okay, so -18. In this instance, you know, we've already illustrated it, but we knew that the smallest zero, or the least great zero of the function is -1, and or excuse me, 1, and so -1 and anything below -1 on this list that we generated here could not work. But when we picked something smaller than the smallest zero for this function, and we see that this last row down here, just to be explicit about it, came out as an alternating set of signs. So we say, okay, so if we plug in a negative number right here and the last row is alternating, then what we know is then -1 has to be a lower bound, okay, a lower bound for our set of zeros up here. So we say, okay, so I know this then. I know that -1 can't work. I know anything less than -1 can't work, so -2 can't work, okay? -2 can't work. -4 cannot work, okay? Less than -1, shoot, -4/3, it cannot work, okay? Well, we say positive 4/3 is still potentially on there, even though we know it's not going to work. But all we're really doing is narrowing down our list of potential rational zeros for this by just knowing some patterns that show up in these things. So maybe it would be worth our time to write a little ditty here. We say upper and lower bounds. Okay, and all, you know, we're going to write out is a couple of conditional statements, and we'll start with this one. We say, okay, so when testing a positive rational number, okay, what's going to happen is this. If the last row in our synthetic array is all positive, okay, what we can say then is then that x value is an upper bound. That is, none of the other zeros that we generated on our list that were larger than that, greater than that, could possibly work, okay? So that's for our upper bound. Our upper bound. Oh, rubbish handwriting. We say, okay, so lower bound. Lower bound necessarily looks like this. We say, okay, so when we test a polynomial, testing a negative rational number. Okay, this only works for rationals. We say if the last row, actually it works for irrationals with this test, but we say, okay, so if the last row is alternating signs, then we say that's a lower bound, okay? Then that x value is a lower bound. So kind of a neat little test to keep in mind here, and I'm actually going to split the screen now because I'm going to come up with a new function. Let's go with, we'll say g of x. So how about we allow g of x to be, we'll go cubic again. We say 9x cubed minus 15x squared minus 15x squared plus 11x minus 15. And so maybe our task is to find all zeros of this function. And again, we could run over to a graphing utility and graph this, but for the sake of this example, you know, I want to point out this new kind of test here. We call it Descartes' rule of signs, in conjunction with our rational roots test and our upper and lower bounds knowledge. Okay, so let's go ahead and start with this. Let's generate our list of possible rational zeros that would necessarily potentially divide into this evenly. So we say the factors of 15 are 1. We've got 3, 5, and 15. Okay. So we've got our list of possible rational zeros for our constant terms. So for our leading coefficient, we say, okay, so 1, 3, and 9, plus or minus. And I'm actually going to leave it. I'm going to leave it in this notation here. It's almost like a set notation. I almost want to put braces around it. But instead of writing this all out, what I'd like to do is, okay, so we could start by trying to divide this by 1. And if that doesn't work, we try -1. If that doesn't work, we try 3. Or if that doesn't work, we could try -3. But it would be really nice if we could take this list and necessarily, you know, narrow it down a little bit. So here's what we're going to do. We're going to use what we call Descartes' rule of signs. And all Descartes' rule of signs basically concerns itself with is number of alternating signs in a polynomial function. So we say, okay, let's necessarily look at the function g of x to begin with. We say g of x, we're going to go through and we're going to look at the signs that this has here. And we said it starts with a positive and goes to negative and back to positive and then to a negative. But just by looking at the number of alterations here, that is, let's go ahead and do that. We say, okay, so it starts off with a positive term and it goes to a negative term. So we say, okay, so 1. There's one alternating sign. We say negative to positive, okay, so we say 2. And we say, okay, so from positive to negative, 3. Okay, so what this basically translates to is this. If in the original function, let's say there are, so many alternating signs. We say, okay, so in this case there were 3 alternating signs. Then what this does is it tells us out of all, of the zeros here, which we know we have to have 3 complex ones, but we say, okay, out of all the zeros that we could potentially find, real zeros, then there can either be 3 positive ones, there will either be 3 positive ones according to our number of sign switches, or we go down by even numbers from this, even integers. So we say, okay, so 3 or 3 minus, we say 2, which is 1, or, if we had, let's say there were 10 sign switches, we would say, okay, necessarily there could either be 10, 8, 6, 4, 2, or no positive rational zeros. But just by counting up the number of alternating signs in the original function, we can necessarily kind of draw some conclusions about the number of positive rational zeros there are. So you might be thinking yourself, okay, so how would I necessarily test for negative rational zeros? And the answer to that is, what we're going to do is we're going to throw in a negative x. And in this instance, for the one time, I will do this, okay? I'm going to actually direct substitute because I want you to see what happens here when we plug in a negative x. We say plus 11x minus 15, and I wasn't supposed to write that. I'm supposed to write a blank, and that minus 15, okay, so we said, all right, we're going to put in a negative x here. I want you to consider the fact that anything that has an even exponent on the x right now is just going to pop back positive, okay? But anything that has a negative necessarily is going to switch the sign that it had started, it started with. So we say now we'd have negative 9x cubed, okay? This would still be minus 15x squared because that negative x being squared, just, it stayed positive anyways. So we say, okay, so this is, this was now, it's now going to be minus x minus 15. But I mean, if you think about it, if we're plugging in negative x's everywhere there's an x, then the only ones that are really necessarily going to switch their signs are anything that have necessarily an odd exponent to begin with. So, just the quick way to think about this is when you're testing for possible negative rational zeros, then we say, okay, then all you need to do is, looking at the original, for example, take a look at this. We say, okay, so we would flip the sign of anything that had a negative exponent. So we flip these two. And anything that had an even exponent, we just leave it alone. And now looking at this, we say, okay, so how many sign alternations are there? Well, we're starting negative and it goes to negative. So that doesn't count. That didn't switch signs. We say, okay, so from a negative to a negative and from a negative to a negative, this never alternates signs. So the cool thing about this is I can already tell you there are 0 possible negative roots. Okay, it's just not going to happen. Okay, and that's just our test for checking for this. And then what's nice about that is now I can go back up here to my list and necessarily say, okay, so I'm not going to test any negatives because it's not worth my time because it's just not possibly going to happen. All right, so we get rid of all those and we say, okay, great.